So today we're going to talk about equilibrium expressions. This is equilibrium video number 3. So you recall I told you before that equilibrium is the state of a reaction when the rate of the forward reaction is equal to the rate of the reverse reaction. An example would be ammonia plus water making ammonium ion and hydroxide. And the double arrow is what we use to symbolize that the reaction is in equilibrium. So to write an equilibrium expression, we first have to have an equilibrium reaction. And we only include aqueous and gaseous substances, no solids or liquids. And that's because solids and liquids are pure substances, and therefore we don't indicate that they have a concentration when they are pure. If you recall, concentration is for mixtures. And gaseous aren't always considered to be pure substances because most of the time they are part of a mixture. So we have that the equilibrium expression, our constant K, sometimes expressed as KEQ. You'll see it written as K, KEQ, KC, also sometimes KP, and we'll talk about some of those differences later on. But mostly we'll see KEQ or just K. And to do that, to write an expression, you do the concentration of the products raised to their coefficients divided by the concentration of the reactants raised to their coefficients. So for the reaction listed here, we would have our products, but since C is a solid, we don't include C. So we have the concentration of D raised to its coefficient little d divided by the concentration of A raised to the little a coefficient times concentration of B raised to its coefficient little b. Again, this is multiplication, not addition. Okay? So what does K really mean? So in a few minutes we're going to learn how to calculate a value for K. K, if it's greater than 1, it tells us that at equilibrium the concentration of the products is greater than the reactants. If K is less than 1, then at equilibrium the concentration of the reactants is greater than the products. Remember, equilibrium means that the rate of the reactions are equal, the amounts of products and reactants are not equal. Alright, I want you to pause the video and complete numbers 1A through D on your worksheet, writing those expressions. Okay? And when you're done with your attempt, then press play, and I'll go over them with you. Alright, so 1A, we have the reaction O3, which is ozone, plus NO goes to oxygen and NO2. So to write our equilibrium expression, we'll write K equals the concentration of products over reactants. Concentration of oxygen raised to its coefficient. And we have to make sure the reaction is balanced. So we have 3 plus 1 is 4 oxygens, 2 oxygens, and 2 is 4, and 1 nitrogen. So this is balanced, so the coefficient is just 1. Times the concentration of NO2 raised to its coefficient, which is a 1, divided by the concentration of O3 to its coefficient, which is a 1, times concentration of NO to its coefficient, which is also a 1. So this would be the equilibrium expression for A. The equilibrium expression for B, we would have the concentration of CO2, because that's the product, and that's going to be squared, because that's its coefficient, divided by the concentration of CO squared, because that's its coefficient, times the concentration of O2 to its coefficient of 1. And so that would be the equilibrium expression for B. Now for C. C is going to be a little different because if you'll notice you have a solid and a liquid. You only have one species that you will use in your expression. So K is going to be equal to the concentration of N2O to the first power because that is its coefficient. The liquid water and the solid ammonium nitrate we do not include because those are pure substances. Alright, so for D, again, this time we have all gases. So we do our products, which would be hydrogen, to its coefficient of a 2, times oxygen, to its coefficient of 1, divided by concentration of water, to its coefficient, which is a 2. And that would be the equilibrium expression for D. Alright, so let's try some calculations. If we look at number 2 on your worksheet with me, you'll see the problem says the concentration of the gases involved in the reversible reaction at equilibrium are known as the equilibrium concentrations. We cannot use initial concentrations. So we must always have equilibrium concentrations. And we'll talk about in the next video what happens when we don't have equilibrium concentrations. But for this video, we're going to focus on just the ones that concentrations at equilibrium. So, in this problem, it tells us that we have this equilibrium reaction, and it gave us these concentrations for the species. The first thing we have to do is write our equilibrium expression. So K is equal to PCl3 to the first power times chlorine concentration to the first power, because both of them have a coefficient of 1, divided by PCl5, which is also to the first power because its coefficient is a 1. And then we can plug in the values of the concentrations. PCl3, problem told us, was 0.0247. Concentration for chlorine was also 0.0247. And that's when we divide by the concentration of PCl5, which is 0.0096. So we multiply and divide, and we simplify and find that our answer is 0.064. Now K does have units, but we don't need to be concerned about what they are. They don't matter to what the expression means. And so since K here is less than 1, that means that there are more reactants at equilibrium than there are products. So what we say is that the reactants are favored because they have a higher concentration. There would be more PCl5 present at equilibrium than the two products. Alright, so I want you to try numbers 3 through 10, and we will go over those in class next time we meet.